It's working. Welcome to the last talk of today's session. Our last speaker is Professor Pavel Putrov from ICTP, and he will tell us about an analog of the volume conjecture for closed non-hyperbolic three manifolds. Yes, welcome.
Thank you for the introduction, and I would like to thank the organizers for inviting me to give a talk at this nice event. So as one can see from my title, so it will be about formulation of a certain version of volume conjecture, which is originally formulated for hyperbolic manifolds. So here we want to kind of have certain analog, want to consider certain analog for non-hyperbolic manifolds. So in a sense, well, we know that the most interesting three manifolds are hyperbolic, so it might be a little bit kind of seem to be not too important from this point of view. But on the other hand, it's kind of more interesting because it's actually a bit harder to formulate it for non-hyperbolic manifolds. And yeah, this is a work which, well, I was actually thinking that it will be already completed by this time. It's a work with Ayush Singh, a PhD student of mine. But yeah, it hopefully will be completed soon. So one of the main motivation can be understood as kind of trying to see how geometric structures of three manifolds appear from the point of view of three-dimensional topological quantum field series. So a priori wise it's non-trivial, so a priori kind of these 3D TQFTs, they have some combinatorial, purely topological combinatorial kind of formulation. So it's not clear what kind of geometric structures, meaning some sort of canonical choices of metrics on three manifolds would appear in them. But from the kind of, we also know that there is a certain geometrization conjecture, well, the Perlman theorem, which tells us there is a very close relation between geometric structures and topology of three manifolds. And the other kind of, since there are some physicists in the audience, the other motivation, which I have not written here, can be understood as follows, is kind of realizing Chern-Simons TQFT for rational level as a path integral. So usually in physics, Chern-Simons TQFT is formulated for like integer level, but we know there is also mathematical construction by Rashid-Hund Turaev, which allows us to define it, define this TQFT for arbitrary rational level. Okay, so the plan of my talk is the following. So most of the talk will be reviewing of notions which are needed to formulate this statement, and I will do this because yeah, there are many people with different backgrounds. And so I will start with reviewing kind of a very brief reviewing of certain geometrization statement, and then I will review quantum invariance of nodes and three manifolds. Then I will review the kind of standard volume conjecture for hyperbolic three manifolds. And yeah, also some recently studied version of closed hyperbolic three manifolds. And then finally, I will make this formulation of its analog for other certain geometries. And then there will be some remarks. So as a warm-up, let me consider kind of this play version of geometrization statement in 2 dimensions. So we know that from topological point of view, the closed-oriented two manifolds are just classified by genus. On the other hand, we know that they have a kind of canonical geometry, canonical geometry in the following sense that they can always be realized as quotient of a certain kind of model geometry manifold M, which is simply connected by some discrete subgroup of orientation preserving isometries. This plus stands everywhere for orientation preserving isometries. And so in particular for G equals 0, the sphere, the canonical the geometric manifold is S2 with a standard metric, and then the group is just a trivial group, which is a trivial subgroup of isometries of S2, which is SO3. For G equals 1, the model geometry is just Euclidean plane. The group of isometries is an extension of SO2 group of rotations by R2 group of translations. And here, the group of isometries is just a lattice, Z2 lattice here in R2. And the generic case is genus greater than 1. The model geometry is hyperbolic two-dimensional space, which can be realized explicitly as a half plane with this metric. And the group of isometries is PSL2R, which acts as follows on this pair of real variables x and y. Okay, in 3 dimensions, the situation is a bit more complicated. So it's not true that globally any 3 manifold can be realized as a quotient of some model geometric space by some group of isometries. But what is true is it's still true up to decomposition into simple pieces. So I'm not going to go into any detail due to lack of time. But basically, roughly speaking, we need to cut this manifold in some canonical way along S2 and spheres and two tori, so that each piece now will be geometric in the sense that it can be realized as a quotient of some M, simply connected M, with some particular metric over the subgroup of isometries. And there are 8 possibilities, which are formulated by the Thurston geometrization conjecture. So the first, the most interesting possibility is hyperbolic 3-dimensional space. Then there is a 3-sphere, Euclidean space, then S2 times R, H2 times R. Then there is the universal cover of SL2R, where we the standard left invariant metric on this group. And then there is this, when M is the nil group, the group of such upper triangular matrices. And the 8th case is the sol group, which is the semi-direct product of R2 with R, where R acts on these R2 as follows. So X, Y is pair. So this is a very brief review of the Thurston geometrization conjecture. Any questions? Okay. So the next step will be review of quantum invariance of nodes and 3 manifolds, and so I will give first the mathematical definition of this quantum invariance of nodes and 3 manifolds, and then I also mention the the physical definition in terms of Chern-Simons theory. But it will be important here that the physical definition only works for special roots of unity. Okay. So the input, so we will consider quantum invariance of knots and more generally tangles and closed 3 manifolds associated to a quantum group, quantum version of group SL2. And well, we will later need to construct the invariance of closed 3 manifolds. This is why we actually need to take Q here, the parameter Q, the formation parameter Q, to be a root of unity. So namely to be 2-case. We actually want to fix Q to the 1/2 to be some primitive 2-case root of unity. Again, yeah, I don't want to go into all technical details, but essentially we define this the quantum group as an algebra given with the generators E, F, and K, where they are related, can be understood as analogues of the generators of the universal Abelian algebra of just SL2 without deformation, Well, the k is related to the standard generator as follows: k is equal to q to the h over half. And this relation, the first line is basically the deformation of the standard relations in the universal enveloping algebra of SL2. And well, for some technical reasons, for when Q is a root of unity, we want to also impose these conditions. And then one can show that this algebra it's not just an algebra, it has a Hopf algebra structure, namely it has a coproduct, co-unit, antipode, which I don't write here. And then the idea is that we want to consider category of its finite dimensional modules. And then there are also technical steps that we want it to be semi-simplified. So we, very briefly speaking, the quotient over all representations which have zero quantum dimension. And moreover, it's a quasi-triangle Hopf algebra, so it has this R matrix. Here there's a universal R matrix. And then we consider a pair of representations, let's say V and W. It gives me this map from the tensor product to itself. And the main idea is to use this, the structure of this category to first kind of define invariance of links and more generally tangles. And this is done by using diagrammatic rules where we label strands by the modules of this Hopf algebra. For example, here's a pair of strands labeled by modules V and W. And then when we consider kind of strands going up, so we associate to them just the modules themselves. And if we have kind of bunch of parallel strands, we associate the tensor product of modules. In particular, if there are no strands, then we associate a trivial module like C. And if the orientation of the strand is going down, like here, for example, we associate a dual model V star. And then we use kind of for this R matrix composed with a permutation, we associate kind of this simple like half braiding diagram. So in general, for each kind of tangle, we associate a map, associate the morphisms between from the modules which we have at the bottom to the modules which we have at the top. Like for example, in these are shown basic kind of building blocks, which we can use them to construct arbitrary morphism corresponding to arbitrary tangle. So this is half braiding, and these are evaluations and covalations. And well, physically, these kind of these strands in this diagram, they correspond to anions in 2+1 dimensional TKFTs, and these morphisms correspond to amplitudes of these processes. And of course, yeah, these kind of basic building, the morphisms associated with basic building blocks should satisfy some relations in order to get self-consistently defined invariants of links and more general tangles. And one of the most important conditions is this Young-Baxter equation on the R matrix. Okay, here by R, I mean the R which was on the previous slide composed as a permutation. And in particular, like if you want to have an invariance on the Serder-de-Meister move, we need this equation on the R matrix. So there are some other conditions which I don't write here, which allow us to define self-consistent invariance of tangles, and this was this was done by Reshtik and Turaev. So this is, for example, how we do this. So suppose we have this kind of three-component link, which we label by, for example, like three modules, V1, V2, V3. Then we can always kind of split this link into these basic building blocks, evaluations, correlations, evaluations, and these half braidings in the blue boxes. And then we can read this diagram from bottom to top. And since we start with no strands and end up with no strands, it should give us a morphism from trivial model C to the trivial model C, which is just multiplication by some complex number. So this gives me a numerical invariant. Well, here it's important to mention that this gives us an invariance of frame lengths. So where we assume that framing can be understood as a choice of non-where vanishing normal vector to which is the component. Like here it's shown in this in green, and we use a convention of the blackboard framing, meaning this framing is a parallel to the blackboard. And in particular, if you take these modules to be reducible models of dimension n1 and 2 and so on, then this numerical invariant coincides with the evaluations of the Jones polynomial of this link, where the colors correspond to dimensions of these irreducible modules. Yes. Sorry, what? Three parameters. Yes, I make some choice. Yes, yes. Any other questions? So yeah, this gives us invariance of lengths. But basically, the output for length, the output is that you have this frame length labeled by, let's say, integers. Each component is labeled by integers, and the output is a complex number, which depends on this choice of my Q, which is the root of unity. Okay, next step is to construct from this invariance of closed three manifolds, and for this we use the fact that closed three manifolds can be obtained by dense surgery on a frame link in S3. And so the dense surgery procedure can be briefly formulated as follows. So for each link component, we remove kind of its tubular neighborhood, and the framing allows us to define the canonical choice of the longitude, meaning there is a one cycle on the boundary of this tubular neighborhood. And so this is kind of can be understood as a one cycle spanned by the intersections of the ray going in this kind of normal direction defined by the framing and the boundary. Okay, we remove this tubular neighborhood, and then we glue in another copy of the solid torus, where we identify this kind of contractible cycle here, the meridian here, with the longitude here. In particular, after the surgery, this red cycle becomes contractible in the new three manifold. And we do it for each link component. So these examples, like for example, if you have something like this, again, I'm assuming blackboard framing, this gives you RP3. If you have something like this gives you the famous Poincare homology sphere. And the theorem of Balik-Roshen-Wallis tells us that actually every closed oriented three manifold can be obtained in this way. And moreover, the theorem by Kirby, and the also version by Van Roerk tells us how. I mean, of course, there can be different frame lengths, which gives the same three manifold up to homomorphism. So the theorem by Kirby tells us what is the kind of the relation between links is such that they must be related by the sequence of moves, certain moves on the inverses. So kind of the simple move is a blow down, where we can remove this unknot, which has this framing like this. And the other move is a handle slice. So we kind of, if you have some link component, we can take one component and kind of pinch it here and slide it along the other component. So here, since we chose the blackboard framing, one can see that this is exactly, so we slide it along the cycle, which is contractible after the surgery. So using these kind of statements, one way to define invariance of closed three-manifolds is invariance, the sort of linear combination of invariance of lengths, which are also invariant under these Kirby moves. And yeah, this is basically what was done by Reshnik and Turaev. And so this linear combination is the following. So we take, so suppose that L is a length, frame length, which realizes my three-manifold Y. And so I take these colored Jones polynomial and sum over all, for each component, sum of, for colors from 1 to k minus 1. And I have this factor where I multiply by this product of quantum numbers Ni for each color. So here capital N is the number of link components. And everything here I evaluate. So here Q is chosen to be this case root of unity. And there, okay, just like this is almost invariant, but one needs to make some correction. So there is some very simple extra factor which I don't write, which makes it actually invariant on the Kirby moves. And moreover, this invariant of three manifold can be extended to a 3D FT functor. So this was a brief mathematical review of quantum invariance of links manifolds. Any questions? Again, the output is kind of for choice of root of unity Q. We get a complex number for scale. And for example, as one can see here from this definition, it's not the kind of the metric of the three manifold doesn't enter in any way. So it's purely like combinatorial topological definition. But our goal will be make some statement which where one can see this geometry in the context of Thurston geometrization conjecture. Okay, mathematically. When it's important, yeah, here, so physically, one considers a choice where this Q is a very special root of unity, like this. But the previous case, one can choose arbitrary case root of unity like this, where S and K are coprime. And actually, we would need like to see the geometry. We would need to consider these general roots. So we consider, for example, for the physical realization of invariance of links is which is a value of the color Jones polynomial root of unity, can be understood as expectation value of Wilson lines supported on the link components in the topological theory, which is classically defined by this action, Chern-Simons action, and we take the Wilson lines in the representations, well, as before. Well, but here we consider this just a classical representation of the classical ordinal SL2, but with the same dimension, N1, N2, and so on. And this, this interpretation of the Jones polynomial is due to Witten. Yeah, here we, the gauge field, well, it's what really the gauge field is, well, we can always, all SU2 bundles on three manifolds are trivial, so we can always globally trivialize them. So the gauge field can be understood globally as a one form with coefficients in SQ2. And for a closed range three manifold, to get invariance of closed three manifolds, we do, well, basically the same thing. We integrate over all SU2 connections now in kind of arbitrary three manifolds. You can see the model ligation transformations. And we don't do any insertions. We just integrate over one form on the three manifold, or possible one form of three manifold with SU2 coefficients. Okay, this, of course, because this measure is ill-defined, this doesn't make mathematical sense. But what one can do, one can kind of look at this integral and make some kind of treat it formally and make some mathematically meaningful conjectures. In particular, one of the first conjectures, which was formulated like this, is usually referred as a symptotic expansion conjecture, which was already appeared in the paper by Witten, then it was kind of refined in paper by Fried and Gomf, and also many works by Anderson and collaborators, which proved it in certain cases. And the idea is that we can pretend that this integral is like finite dimensional integral, so we can do a kind of stationary point approximations. It's an exponential integral. So then from this point of view, we should get some sort of sum over classical stationary points, which are given by critical points of Chern-Simons functional, which are known to be flat connections. And after gauge transformations, they classify by Holmes from pi1, the fundamental group of three manifold, to SU2, modulo the adjoint action of SU2. So we would expect the expansion in the limit when k goes to infinity, we expect this to behave in this form. So it's a sum of connected components of this moduli space of flat connections. And in each term, we have an exponential term where we have the critical value of Chern-Simons functional times some series, formal power series, well, which can be defined for arbitrary formal variable h bar, but here we kind of, for this formal variable, we put 1 over k. And this makes as a asymptotic series when k goes to infinity along the integers. Okay, and okay, next I would want to proceed with the review of volume conjecture. Any questions about this part? No, here, yeah, some of our connected components. Well, I just put it into this first coefficient here. Any other questions? Okay, the first kind of version of volume conjecture was formulated by Renat Kashaev. It was formulated for hyperbolic knots in the three sphere. Hyperbolic means that the kind of well, complement in a sense of some cusp manifold can be, it has a global hyperbolic geometry. And it can be formulated as the, well, there was a slightly different formulation later by Murakami. So one version can be said that of this conjecture can be put in the following way. So we take this color, we just take one knot, so, and we consider colored Jones polynomial, so there's a single color index, and we take color to be the same as the level, and we take as logarithm, and we take this ratio, and we take k to infinity, and the limit must be some special value of Chern-Simons functional on the what is called geometric SL to C flat connection. So here, before we consider it SU2, the Chern-Simons functional, sorry, I'm going the other way. So here we consider Chern-Simons functional where A was considered kind of one form with SU2 coefficients, but we can analytically continue this expression by just using the same formula where instead of SU2 we have here SL2C, and we just use the same formula. Sorry. Okay. And this geometric flat connection is can be described as follows. So it's well, as I mentioned before, the flat connections, they correspond to maps from pi 1 to our gauge group. Here is SL2. So here the have a for geometric hyperbolic manifold, we have a canonical inclusion of fundamental group into PSL2C, because this is a group of isometries of three-dimensional hyperbolic. Because here the quotient is with respect to the subgroup of isometries. And then one can also argue that there is a canonical lift from PSL2C to SL2C in this case. And why is it called volume conjecture? Because like imaginary part of it is known to be the hyperbolic volume. So the volume with respect to the hyperbolic metric induced by this quotient. And so if you consider the absolute value part here, the imaginary part is what is plays role. Questions? Okay. Now I want to review. Yeah, this is more recent development. I want to review the version of volume slash quantum modularity conjecture for closed hyperbolic three manifolds. So in this version, kind of the most general version up to date was appeared in the paper by Campbell Wheeler in the end of the previous year. But it was like in this version, it was checked basically for a single example, but it's a non-trivial of a closed hyperbolic manifold. And so this, let me mention that before I explain something here, let me also mention this is in a sense a combination of kind of volume conjecture for closed hyperbolic manifolds which appeared previously by Chen and Yang, and also quantum modularity conjecture for knots, hyperbolic knots, which was formulated by Zagir and also was studied a lot by Zagir and Grufalidis. So the statement is the following. Now we consider our quantum invariance of three manifold, which is usually referred to as the Witten-Richter-Reif invariant. But now we want to consider general root of unity. Not in the symbolic expansion conjecture, we consider it S equals 1. And here it's important that we take a general root of unity. So we consider general S. We're going to consider, for example, fix S and take K now to be infinity, but it goes along coprime, pair integers which are coprimes with S. And then the limit will be of the following form. So the leading term given by the Chern-Simons value of these geometric flat connections which appeared before. Then there will be the asymptotic expansion type of piece, which is similar to what we had in the standard asymptotic expansion conjecture, which can be understood as kind of we have formal power series of h bar, where instead of h bar we put this kind of s over k. And there is this non-trivial piece which is the same as the double rate invariant, but with modular transformed root of unity. And this is why this is referred as a quantum modularity. But this is kind of modularity of the function which is only defined for on the rational numbers, not arbitrary kind of complex parameter tau. And well, one can ask how this is kind of consistent, can be consistent with the asymptotic expansion conjecture, because in the asymptotic expansion conjecture, we only saw the SU2 flat connections. But here, this is, we have some sort of appearance of SL2C, non-trivial SL2C geometric flat connection. Well, this is consistent because if I take S equals 1, here this will be just 1. And this is, we use a normalization where this is the double rate invariant when Q is 1 is just 0. So this term goes away and the subleading terms start playing a role. And the subleading, this is what is seen in the asymptotic expansion conjecture. Okay, and now basically we want to make a similar statement for non-hyperbolic manifolds and the kind of complications that for non-hyperbolic manifolds, this is not like for hyperbolic manifolds, this is dominating because this has non-trivial imaginary, negative imaginary part. But for non-hyperbolic manifold, all SL to C flat connections have Chern-Simons, value Chern-Simons functional be real. So we have to consider them all simultaneously. Okay. So to avoid some technical details, let me assume that C manifold is an integer homology sphere. So the first homology group is 0. And assume it's geometric, so it's globally given by the quotient of m divided by gamma, where m is one of the eight Chern geometries. So here I am using some physical normalization of the double Ratin invariant, and in this normalization, up to some simple factor, it is known to be a polynomial in Q, this root of unity. But this polynomial is important, which follows from the some results by Habira. But the polynomial depends on the choice of the order of the root of unity. Then one can make the following statement that we consider double Ratin invariant with arbitrary root of unity, and we take again the limit k goes to infinity along co-primes with s. Then we have we write it as a sum over all components of all SL to C flat connections. And for each component, we have this following term. Again, there will be an exponent of k divided by s, the value of Chern-Simons functional. There will be again this asymptotic series term. And then there will be a prefactor, which is a certain polynomial with integer coefficients in Q tilde, where Q tilde is this modulo transformed. So if we take, now it's important to consider general root of unity. Q tilde will be 2 pi r k divided by s, like here. And the statement that there is a special component here for which this polynomial coincide with the polynomial which appears with double Ratin invariant in the double Ratin invariant. Basically the same up to this simple prefactor. One of the terms this polynomial is the same as for double Ratin invariant. So in particular for hyperbolic manifolds, we immediately recover this statement by Wheeler, because this there will be a single dominating term for these geometric flat connections, and we get that this indeed this polynomial is the same as that. But in general, we have to keep all these terms contribute on the same level, so we have to keep all of them. Okay, but one can ask, what is the kind of geometric meaning of this special flat connection in general? So we want to define some special map, canonical map from pi 1 to SL to C, right? This is from the point of our flat connection should be represented by one of such maps. So what we want to do is the following. So, well, we know that if the manifold is geometric, then the fundamental group can be identified with the subgroup of isometries of one of the 8 certain geometries. So what we want to do, we want to kind of compose this map with a certain canonical map from isometries to PSL to C. And for hyperbolic cases, this map is basically trivial. This is identity map, right? But in general, this is not going to be identity map. So okay, this is a kind of a list of proposals what such map should be for geometry. So let me not go, like consider all of them. Let me focus on this case, where the geometry is universal cover of cell to R. Then the group of isometries. Let me write it here. So the isometries of universal cover L2R is an extension of by R of PSL isometries of hyperbolic plane. This is because this universal cover L2R can be understood as R vibration over H2 locally, and this is isometries of H2 is PSL2R. So this means that there is a canonical map to PSL2R, which can be included in the PSL2C, and then there is some argument can be made that it can be lifted to double cover SL2C. And then we can make, we have a theorem that the conjecture is true for the vibration over S2 with up to 3 exceptional fibers. This can realize these 3 different geometries. And the proof is basically by explicit computation of the asymptotic expansion for generic root of unity. And there are some independent computation of these values of Chern-Simons function for geometric flat connection. For like this SL2R case, which I removed, one can actually find in the literature, like one can find the results, all the results in the literature, which combination of this result gives you actually this value. And you have some evidence in other cases. Okay, so this is the kind of main content of my talk. And after that, I have some remarks, mostly physics type of remarks. Are there any questions? Yes. Yes. Yeah, they are contained in this part. Yeah, the leading term is a derived version. Yeah, but they can. This kind of control part is actually this stuff. Yeah, this is basically the same. This part is the same as in the usual asymptotic expansion. Well, I think I should be able because like derive error is basically absolute value of restricted derive square. Yes. No. One needs to take s not equal to 1 to see non-hyperbolic. Yes, s equals 2 is Chen Yang. Yes, XL2 you already can see the volume. Because this factor is something simple. It's like WT invariant at -1, which is some very simple number. Yes. Yeah, this is non-zero. This is non-zero. When s equals 1, this is 0, and so this goes away, and you see non-hyperbolic. So this is other flat connections. Or default of what? Same manifold? No. Okay, very much. Well, yes, there is some. There is a kind of holomorphic quantum modularity. Yeah, I should mention the holomorphic quantum modularity was previously observed for certain analytically continued version, where we kind of take Q to be some complex number with absolute value less than 1. And this quantum these kind of analytically continued versions, usually referred as Z hat or GPP invariants. Yeah, this kind of homomorphic quantum modularity was studied in various papers. However, geometric meaning of this special Fourier connection was not discussed there. Okay, the second. Okay, yes, this. Second remark is what is the interpretation of these polynomials? So we had this in this asymptotic expansion for general root fields. We had these polynomials with integer coefficients of q tilde. So they have the statement is that these coefficients of these polynomials, which are integer numbers, have the following meaning. The meaning is the following. So we can, like for general root of unity, we can realize the double Rt invariant as some sort of contour version of the path integral, where we we want to integrate something like this. Of course, the usual case when s equals 1, and we have invariance under all gauge transformations, really large gauge transformations, so we can do this. But what we want to do in the case of the rational level, we want to consider instead, we want to go to SL to C connections, and we want to model gauge transformation, but then we consider the S-fold cover. Or equivalently, we can say that we only quotient over large gauge transformations, which has a degree which is multiple of S. And then we take a certain contour gamma in this kind of infinite dimension complex space. Well, since it's the S-fold cover of this space of SL to C connection homologous transformations, each critical point has S lifts. And well, the integral can be uniquely, any contour integral can be uniquely decomposed into Lefschetz symbol contours. And so for each flat connection we want to specify S integer numbers, which are coefficients of decomposition of the contour with respect to those Lefschetz symbols. And the same as that these S numbers are exactly the coefficients of this polynomial. Again, this final remark is that this quantum modularity has something to do with the fact that the analytically continued version of this should be realized as a partition function of a 6D to 0A1 superconformal field theory on the 6-dimensional space, which is a product of Y3 T2 times R plus, where this Q, the quantum parameter, it plays the role of the norm of the two torus. However, well, at least in my opinion, this so far has not been made precise, even by theoretical physics standard. And precise, I meaning to actually like derive this quantum modularity formula from physics. And this is mostly because the fact that the boundary conditions at this kind of R plus is hard to analyze explicitly. Well, mostly because this is some non-Lagrangian theory. Okay, that's it. Thank you. For the quantum group, it doesn't matter what is. It's just important that Q is a case primitive root of unity. It's just important that S and K coprime.
So the dimension of this irreducible module, they don't depend on S?
No. Well, actually, this you can say that everything, like in there, everything is related by some sort of Galois transformation, like we checked on these roots of unity.
Which
Galois transformation.
For values of S which are larger than 1, don't you need lift, integral lift of the flat connection? And if you do, is there any insight into geometric meaning of the lift?
Well, again, we need this lift if you want the path integral interpretation, yes. Yeah, here we need this lift, and that's why we need this specify S integer. Like for each flat connection, we need to specify S integers. And the statement basically is that for the lift of this geometric flat connection, this these integers are the same, somehow happen to be the same as the integers which appear in the this polynomial, which gives you the double routine variant itself, which is for integer homologous sphere, it's known to be a polynomial, this integer coefficient. But here, yeah, I'm not here. I'm just making the conjecture about the expansion has this form where the sum is over. Here, the sum here I don't need to leave. This is just without lifts. It's kind of the choices of lifts. They're all packaged in this in this polynomial.
So for some S, we know that TKFT is non-unitary, and for some other S, we know that it's unitary. So from the path integral interpretation, can you see like what's special about those unitary S?
A good question. Yeah, because like yeah, we don't since it's not since it's some weird contour integral. For me, it's actually not even obvious that it should define some local quantum field theory. But yeah, we know from the Rishkin-Reich construction that it does. Yeah, even locality is not clear because this is not usually how you write the like path integral. I don't know. Yeah.
Situation. So, and for modular quantum group, you have different class of representations. Did you consider this?
No, short answer is no. Yeah, here this Q tilde appears in the sense that this kind of modular transform version of the Q, like in the kind of yeah, usually, I mean usually the modular we consider Q is like for like normal modular forms, not the quantum modular forms. We consider a function of tau where the imaginary part tau is greater than 1, so Q is less than 0, and the kind of Q tilde is e to the 2 pi I divided by tau. So this is tau tilde times 1 over tau. And here we, instead of we consider tau to be actually a rational number. So imaginary part is actually 0. So it's just in this.
So for irrational numbers,
Okay.
just continuous series instead of one-dimensional representation series.
Yeah, I have not considered. Yeah, I have not considered this relation.
So for the other Chen-Simons, for the other geometries, where does the Chen-Simons take value?
Well, it's always actually for all non-hyperbolic, it's a rational number.
A rational number.
Yes.
So it can be real number.
Yeah, it's in particular it's a real number. Yes, for all this except this, the consignments is always a rational number.
Oh.
Yes. And here, yeah, it's not just complex. It's more, it's transcendental.
I see.
So it's a big difference.
So, question. Let's thank our speaker again.